I'm one of the few people in the conference, I suppose, who is going to say images and videos are special, or visual data. And that is the case because they are rich in information. And data science and ML techniques have now helped companies in different domains like smart retail, smart agriculture, medical imaging, help unlock insights that these data types contain, um, and enable better customer experience, which can give them a competitive edge if done right. Well, that has naturally led to an increase in the amount of visual data that needs to be managed, how frequently it is accessed. So then the question is, do we know how to do it right? And, and the reason that's a question is because images and videos can be large. An image can be 2 GB large. And then there are millions of, they usually occur in large quantities. So, you have millions of images and video. The processing requirements of this data type is different. So you think about resize, rotate, sampling videos. The computational intensity of these operations can be quite different than if you were doing sum and average on numerical data. And lastly, the metadata forms a key piece in being able to manage or access, and it describes not just the objects, but what's contained in the object, where did the information come from. So let's see if we have a handle on managing this data. We'll imagine you're a data scientist who has to retrain a model to classify who has to train a model to classify thousands of new classes on hundreds of thousands of new images that were just dumped in some cloud bucket. So typically today, particularly in a large company, what this would mean is first you have to find out which table the metadata got dumped in. Then you have to get permission to access the table. Then you're going to write some complex metadata query, like with a bunch of joins to actually get the URLs of the data for where it lives. Once you have that, it gets worse because now you have to make sure that you have access to the data buckets. You allocate a big enough VM so that you can download all those images on your local machine and are able to process them. Then you go ahead, download them with the URLs that you got access to, and maybe to prepare the data set, you're going to have to do some pre-processing. That code is just to make you realize that it actually gets pretty complex, particularly as you go with like a lot more data or if you start dealing with videos. So after you've spent maybe hours, sometimes days, you finally can actually go ahead and train and classify your models. This was the data management status quo that we encountered when Intel started their research center along with Carnegie Mellon and Stanford to design visual cloud systems. My co-founder and I were really excited that, we're going to get to work on cutting edge research in deep learning and computer vision with all these academic researchers, except we were responsible for managing this data. It's not like we could pull some off-the-shelf tool, because there isn't a database that understands images and videos. And so we spent most of our time doing that. And as we talked to more and more data scientists and ML engineers who were trying to work with this data, we realized how hard the data infrastructure was and how long it took. So since we were going to solve this problem for ourselves, we figured we'll solve it well and make it available to different people because, and that kind of prompted us to spin out ApertureData to prove that just because your data is unstructured, it should not be onerous to deal with it. Now, after hundreds of conversations with companies using or intending to use visual data, what we have realized is just how complex the landscape is for dealing with this data type. It's not just that you have to deal with image and video files when you're trying to do data science or machine learning. You also have to deal with other data types, like there is application metadata, there are annotations, sometimes there are embeddings, sometimes there is pre-processing libraries that need to go along. And it's to deal with these products, you have to deal with these in different, to deal with these data types, you have to deal with them through different products because there are different products designed to handle each of these data types. Now, naturally, that means this lack of interoperability means you have to do the translation among the various components yourself, which not only causes performance delays, but it also makes data lifecycle management very painful. It's also, if you imagine that you have to pull data when you need to prepare this data for machine learning, you need to pull these data types from various components, and that means very long engineering delays. We have actually spoken to data scientists who are reluctant to refresh their data sets often or change the metadata or update the metadata schema for fear of losing more and more time not understanding their data and being productive. Finally, the fact that you build these point solutions means a lack of reuse, which further delays how you achieve your business objectives. Now, let me just walk you through a classic development sequence to really paint a picture of how a DIY system evolves and becomes extremely complex as you're just trying to get from input data into something meaningful like trained model or a data you want to display or some recommendations. So naturally, you start out with some images and metadata or videos and metadata. They need to go into a cloud storage bucket. You might put the metadata into some database of your choice. Very often, you require labels to start training. And so you might bring in manual or automatic labelers. They will want access to the data, and then they'll provide you with these annotations in some formats that you either dump in other cloud storage buckets or maybe you ingest them into database so you can do searches based on labels. After that is when the DIY or do-it-yourself scripts come into picture that pull images and the other information together to feed them into the ML frameworks or front ends for display. Very often, you might need to pre-process this data because maybe a neural network requires lower resolution images. Very frequently, you might also want to index embeddings that describe the content, which means then you have to bring in libraries for indexing them and doing similarity search. So the spaghetti on purpose is to prove a point how natural development leads to this extremely complex, glued together system, which can be brittle and hard to reuse, not really an elegant way to solve a problem. And imagine what happens when you are when you start putting in other use cases and more data and multiple users. So really what people have been wanting is a single unified approach to deal with all these data types. If you could have a holistic purpose-built system that could address all these things, it would mean enhanced productivity with simplified data engineering, much faster ML iterations. Such a system would be able to evolve as your use cases evolve, and it would also be able to scale with data growth, all without disrupting any of the user pipelines. That's, of course, what we offer with ApertureDB, a purpose-built visual data management system for visual analytics. So ApertureDB natively supports images and videos, which also means that we support pre-processing operations near this data. So you can ask us to resize, rotate as you are accessing these data types, given the range of machine learning use cases that we were targeting. Now, the other thing was, how do you store or model the metadata? So we looked at a lot of different applications ranging all the way from simple COCO dataset, which is what a lot of ML researchers start out with for training, going all the way to complex medical imaging and autonomous driving applications. What this metadata looked like in most cases was a graph. It was more specifically a property graph with entities and relationships and then key value properties on all of them. And sometimes you could group them together by classes. So that's why we store or we manage the application metadata as knowledge graph within ApertureDB. And given that we were always thinking about machine learning applications, we manage bounding boxes or annotations as part of this metadata to allow you to do label-based searches. Now, a third aspect of search, because the uniqueness of visual data is that feature vectors or embeddings can help you define the content in these things. So that allows you to do similarity searches based on the object similarity. So the third thing we support is indexing n-dimensional feature vectors and do similarity searches. Now, all through, we didn't want our users to have to access these different components separately. So ApertureDB also has a query engine or orchestrator that allows, that takes in queries from the user, redirects them to the right components in the system, combines the results, and returns a coherent response to the user. What it exposes to the user is a native JSON-based query API, which can then be used by the machine learning pipelines or end users to add, modify search, visual data, and metadata, to perform on-the-fly visual pre-processing, to change the annotations and feature vectors, or to do more machine learning kind of tasks like maybe taking data snapshots. Now, our design choices have direct impact on the performance. So, a common query in these cases, for example, to prepare a training data set, is to search using some metadata criteria, access the images, and very often like resize or rotate or do some augmentation. Now, all of those things are supported by ApertureDB through its unified API. And in order to compare performance of the DIY system that we had heard people talk about, we created our own where metadata was serviced by Postgres, the files were served by Apache file server, and then we pre-processed the images using the popular OpenCV library. We evaluated evaluated the performance using queries on YFCC 100 million image and video data set, and ApertureDB was 35 times faster compared to the DIY, depending on query complexity, and 15 times faster on average. Now, because we can pre-process images and videos where they live near the data storage, we get a welcome reduction in network transfer very frequently, because the common use case is you store high resolution, but your neural networks expect lower resolution data. So what I'm saying here is, because of our design choices, ApertureDB makes sure that the data part is really fast and doesn't become a bottleneck. Now, it's important to manage the data and metadata, but it's also important to seamlessly integrate in the data science tooling ecosystem so that it becomes easier for data scientists to adopt. To enable that, ApertureDB can store and access data from cloud storage, or it can manage the data itself. We also provide client libraries for C++ and Python application development. And there's a good bunch of tooling around. So for example, we have very fast concurrent loaders to ingest data very fast into ApertureDB. We also provide dataset loaders to feed the data into machine learning frameworks like PyTorch. We also provide REST API so that we can easily integrate with labeling frameworks or front ends that people might have. And we have our own web UI to enable easier access. And then finally, one of the missing pieces that we have noticed is that there is a lot of data science research tooling. But in order to be able to move the same pipeline into production, you require some SRE style requirement. You have to fulfill them, like you need authentication, access control, monitoring, logging, and this is all the stuff that we've built into ApertureDB. And what we have learned is, because infrastructure like ApertureDB can actually be, it can take a long time to build, especially if you have to provide all that with the right API. So one of our customers told us it would have taken them more than 6 to 9 months to build this, needed 3 to 4 more infrastructure engineers. And they were able to, using ApertureDB, create a much simpler ML pipeline. We've also tested it for large scale because of the design choices, and we were able to scale it already to more than 1 billion metadata entities and more than 300 million images. Now, with ApertureDB, of course, data scientists can move faster. We've been targeting to help them, build their recommendations, classification, and all those pipelines fast through faster searches. But we also help a lot of other personas. For example, now the infrastructure people don't have to maintain 4 or 5 systems. They have to maintain 1. The data engineers feel there's a simpler lifecycle management because ApertureDB takes care of maintaining consistency among all these other components. Data science managers can see a lot more coordination among teams, because now everyone has access to a common visual repository that they can work off of. And then, of course, there are SRE style requirements for any production deployment, which we also address. So now let's see, have we really helped and changed the data management experience for data scientists? Now, as a database, naturally, you expect it to help you understand the data types it manages. So we make it very easy to find what your metadata looks like so that you can actually start building queries. And then data is the other thing which we help you manage. So of course, you should have an easy way to navigate what's contained in your data. So we have easy visualization to be able to see what's in the data, what your images look like, maybe the bounding boxes that you might have put on them. Now, you remember at the beginning, I showed you this pipeline where in today's systems, you had to do a lot of complex different steps, except with ApertureDB, training and classification literally becomes a matter of writing a simple filter query and just feeding the data set into PyTorch, and you can start training or classifying. Another interesting use case we learned of from our customers is that it helps them debug their data set fast. If you can just turn a Boolean on or off, you can actually just simply show what do your bounding boxes look like, what do your segmentation masks look like, which makes it really simple to understand what's going on with your data set. Then maybe you wanted to search not just with keywords or labels, maybe you wanted to search without keywords, and that's where embeddings come into picture, because that's yet another way of searching visual data. And so we also have very easy similarity search to enable you to search with, find similar near neighbors. I wanted to conclude with this slide to show. Oh, I wanted to conclude. Wait, hold on. This was my. Have I been going on a different slide? Sorry. I wanted to conclude with this slide to bring back that, how if you have a purpose-built system, you can actually start focusing on your machine learning and data science use cases instead of spending time wrangling data types. So yeah, if that the QR code should give you some links to access and go to our demo trial and other links. Thank you so much for listening. And if you have other questions, please find me during the networking time. Thank you.